Okay, welcome everybody. So next week we'll have a quiz on some R material that you can find here under this account name, yes to that. And you'll see here R in action, chapter so on. And I'm going to ask you to go through the videos in chapter 2. So there's actually 10 short videos. So, or you don't have to do it that way. You can find the book R in Action in the reserve section of, or in the library, I'm sorry, at APU's library, and you can just read it. Or you may be able to get a copy yourself on the internet. So, in any case, you can do it that way, or you can go through the videos. But, one second, let me fix this. So you can go through it. Anyway, it's just on chapter 2, and you can go through my videos. There's like, as I said, there's 10 of them that are short, so you can go through them here. They're called R in Action, chapter 2, part 1, part 2, part 3, part 4, part 5, part 6, 7, 8, 9, and 10. Okay, so we'll have a quiz on that material next week, and that'll probably be the end of our work. And today we want to go through chapter 5. Before we do that, does anybody have any questions?
Do we have Meeker?
No, not in this class. Okay, that's good or bad, I'm not sure. Usually it sounds good, but I'm not sure. Some people, well, anyway, it doesn't matter. Anyway, we're not having it. So, any other questions? Any other questions? Okay, so that quiz will be at the beginning of class next week, so you should be logged in long before the class, before 10:35, you should be logged in, otherwise you won't be able to take that quiz, because you won't have that long to do it. Okay, so today's topic is chapter 5 is discrete random variables and their probability distributions. So that probably doesn't mean anything to you. So, so now that you know a little about probability, do you feel lucky? If you have $20 to spend on lunch today, are you willing to spend it all on $21 lotto tickets to increase your chances of winning? So how about if, they sell, what is it called in Japan? Takarakuji? No. Takarakuji. So you can go down in Beppu. I don't think they sell it on campus, but you can do it down in Beppu, and you could take all of your money and, of course, bet on Takarakuji. So what do you think are the chances, how good are the chances of you coming out ahead when you do that? Okay, so that's what they're talking about. So that obviously is a question that has something to do with probability. So we're going to talk about these two concepts. And here we have survey of people, asking them how many vehicles do they own, like one car, 2 cars, 3 cars, 4 cars. So this is owned by families, not people, okay? So the total number of people surveyed was 2,000, okay? And 30 of those didn't have a car. And 850 had 2 cars, and so on. And here we have the relative frequencies, so 30 out of 2,000, and 850 out of 2,000, so 1.5% and 42.5%, right? And so on. And when we sum this up, we get 2,000. When we sum this up, we get what? We get 1, right? The relative frequencies, when you add them all up, you get 1, okay? All right, now we have a very important definition. So basically, we had several words that I asked you to learn to become accustomed to. And what were those words? We had several words. So I asked you to become accustomed with the word experiment. I asked you to become accustomed to the word sample space and event. Okay, and there's one more word, maybe 1 or 2 more. This one, random variable. Okay, this is a very important word to get used to. Okay, a random variable is a variable whose value is determined by the outcome of a random experiment. So we know what is meant by an experiment. That's some action, right, where you don't know the outcome. And a random experiment, actually, I don't know what the difference is between experiment and random experiment. So I'll just leave it as an experiment, okay, where you don't know the outcome. Okay, is that okay for everybody? Random variable is a value that is determined by the outcome in an experiment. So let's say I toss 2 dice. Let's take what's an example of this? So suppose I toss 2 dice. That's the experiment, and I can say that the random variable might be the sum of the 2 dice. So the random variable might be the sum of those 2 dice. So we'll usually use a capital letter for a random variable, okay? So the experiment, the random experiment is rolling 2 dice, and then we have a variable x, which is the sum. So that can take on many different values, right? What, for example, what's one possible value that the sum could be? 6 or 5, right? By this, you know, if you got a 2 and a 3, the sum would be 5. If you got a 6 and a 6, the sum would be 12, right? Okay, so that's an example of a random variable. Okay, definition: a random variable that assumes countable values is called a discrete random variable. Okay, here's another experiment. Let's say y. Let's say we do an experiment where I choose a person from this room. Okay? I choose a person from this room, and I ask them, how many hours did you sleep last night? Okay, so let y be number of hours that person slept. That's right, it's fine, okay. Anyway, so what kinds of values can that be? So I choose this person, and I say, how many hours did you sleep? And what can they say? I slept 7 hours. And then I choose another person, they say, I slept 7.2 hours. And then I choose another person, and they say, I slept, 6.11111. Now, it's unlikely that somebody's really going to say that, but we could kind of say that, right? Whereas, if I asked you about x, you can't say that the sum was 4.22222222222, can you? the sum of two dice is only 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's all. Right? Does everyone understand? But the number of hours that you slept is not like that, right? So we have to make this distinction mathematically because there are certain techniques that we can do with one type of random variable when we just have a finite number of values as compared to things that we can do with a random variable that can have an infinite number of values. Just mathematically, turns out you just can't do the same things with both of them. So they want to make this distinction now before we get started, just so that you recognize it now. Okay? So we have discrete random variable. So this type, the number of hours that someone sleeps, is called a continuous random variable. And this one, the sum of the two dice, is called discrete. Okay? Now there's two types of discrete actually, but maybe it's not too important for us to worry about it. But this is also discrete. So even though it's infinite, it's still called discrete, but we don't really have to worry about it. It doesn't matter that much in our class. But mathematically they say that's discrete, but it doesn't matter. Okay? Any questions about this? So a discrete, so what's, from these two random variables that I just mentioned, which one is the discrete one? From these two that I just mentioned, which one is the discrete one? What? The x, right? The sum of the two dice is the discrete one. The other one is called continuous. So this chapter, chapter 5, is about, we handle the case of discrete ones. And then in chapter 6, we handle the case of continuous ones. Okay? So how about these examples of discrete random variables? The number of cars sold at a dealership. Is that discrete or continuous? Discrete. Why? You can't say I sold 36.88888888 cars, right? That doesn't really make much sense. The number of houses in a certain block, right? That's just a discrete number. The number of fish caught on a fishing trip, right? The number of complaints rather, that received at the office. So, you know, when you have a company, let's suppose you're Amazon.com, you get 3,000 complaints today, but you don't get 3,000.88888 complaints, right? Okay, so these are all examples of discrete random variables. Definition: a random variable that can assume any value contained in one or more intervals is called continuous. Okay, so I already explained what continuous. Here's a definition of continuous here, but I gave you the idea already. So every point on this line represents a possible value of x that denotes the life of a battery. Okay, when you have your phone battery, you can say how long did your phone last today, right? And it can be anywhere from 0 to 200 minutes or something like that, right? So it can be any number in here. So that's called a continuous random variable, okay? There's an infinite number of points on this line. The values represented by points on this line are uncountable. Okay, so these have technical definitions, but we don't need to worry about it. It's pretty clear what they're talking about. The height of a person, right? We can measure, that's continuous. The time is continuous. The amount of milk in a liter, or something like that. The weight of a fish, the price of a house, okay? These could all be considered continuous random variables, okay? So now we talk about, now in section 5.2, the probability distribution, that's a new word. The probability distribution is a new word of a discrete random variable. So we don't know what that means, but we do know the last part, what we mean by a discrete random variable. So here's a definition. The probability distribution of a discrete random variable, it's actually a list. You can think of it as a list. It lists all the possible values that the random variable can assume. So, okay, let's go back to our example here. Which one of these was discrete, x or y?
X.
X. X was what? The sum of the dice. So that was the discrete one. Okay, so what they say is we're going to list all the values that x can take. So what are the values again that x can take? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? How many is that, by the way? 11? Yeah, I think that's 11. Okay, so there are 11 different values that x can take. And then next to that, in this list, we're going to compute the probabilities for each of those. Okay? So it's going, well, okay. So is there any questions so far? Okay. Recall the frequency and relative frequency distributions of the number of vehicles owned by families given in table 5.1. I don't recall that. Did we? We didn't go through that here, right? Oh yeah, we did, sorry. Here it is. Here it is, right? Okay, so remember this, this table, right? So we have the relative frequencies, okay? So if how many people are in this group? 2,000 people in this group. If I select someone at random, what is the probability that they don't own a car? From these 2,000 people, I'm going to select someone at random. What's the probability that that person doesn't own a car? 1.5%. Right? Isn't that 1.5%? Or 0.15 if you prefer to say it that way. But you can also say 1.5%, right? Okay, so either way, it doesn't matter. But once again, if I select someone at random from this group of 2,000 people, what's the chance that they don't own a car? 1.5% or something like that. Okay, and how about what's the chance that they own 4 cars? 8%, right? Okay, so now you can make a random variable out of this because you know the probabilities for each of the possible values of this random variable. Okay, sorry. One more thing to say before I say that. And that is, this is a random variable. The number of vehicles owned. Okay, what are the possible values for this random variable? 0, 1, 2, 3, 4 for this group of people. Okay, everyone understand? So this is a random variable. Now, what are the probabilities for these? What are the probabilities for this here? These are the probabilities, right? Does everyone recognize that? Everyone agree with that? So if I just block out, if I ignore this center column, then this column and this column are a list, which we could call the probability distribution for this random variable. Okay, so I erase this column here, just get it out of the way. Okay, so I just have this column and this column. That's called a probability distribution for this random variable. So what is the probability distribution? It's a list of the possible outcomes and their associated probabilities. Okay, that's what we mean by a probability distribution. So I could ask you, what's the probability distribution? Let's call this X. The number of vehicles owned, we'll call it X. So I could ask you, what's the probability distribution for X? And you would just put this up there. You just make this table for me. Okay, and that would be the answer. Okay, so what is a probability distribution for a random variable? It's a list of all the values that random variable can take, and their associated probabilities. Okay, does that make sense? That's what we mean by a probability distribution for a random variable. So now you do know what it means. Okay, so we said here, the name of this section is what? Probability distribution of a discrete random variable. Now, I said you know this part, but you don't know this part, but now you do know this part. Okay? So the probability distribution of a discrete random variable lists all the possible values that the random variable can assume and their corresponding probabilities. Any question about that? Okay, here, recall the frequency and relative frequency distribution of the number of vehicles owned by families given in table 5.1. That table is reproduced below as table 5.2. Let X be the number of vehicles owned by a randomly selected family. Write the probability distribution of X. So let's write it here. Okay, so here's X, the different values, and here are the probabilities, and this is called the probability distribution, okay? And of course, the sum of all, oh, and I'm sorry, we call these P now, instead of relative frequencies, because they all also are the probabilities, right? If you select someone at random from this group, they are the they are the probabilities, right? And of course, the sum of all these P's has to equal what? 1, right? The sum of all these, so if you add this plus this plus this plus this, you have to get 1. Anybody have any question about that? Okay, good. And the next one is about Mitsubishi UFB Morgan Stanley. Quality for you. Somebody's looking for a job. But if you want to get a job, you have to know statistics. Especially in this company. Really, that's true. Actually. Or it's going to help anyway. Okay. So, I don't know, who's that? Okay. Well, at least they weren't looking at something else. Okay. I appreciate that you're looking at Morgan Stanley. But it might be better to make sure you know this. Okay. Anyway, 2 characteristics of a probability distribution. So look at this and this. Are these true or not true? What does this mean, this part here? These are those probabilities that we just mentioned, right? Those are the probabilities that we just mentioned. So what about number 2? What does it say? If you sum up all the probabilities for all the possible values of X, you have to get 1. That's always true, right? Doesn't matter what. So, of course, these probabilities could actually be different, right? Maybe for a different group of people, these probabilities will be different, right? Everyone agree with that? But if you sum them up, are they not going to equal 1? No, they're still going to have to equal 1, right? Maybe this will turn out to be 2% instead of 1.5%. And maybe this will turn out to be 20% instead of 23.5%, right? But still, no matter what, when you add them all up, you better get 1 or there's something wrong, right? Right? If you add them up and you only get 80%, there's something wrong, right? Something went wrong. It's not correct, right? So that's what they say here. When you sum them all up, you have to get 1. No matter what the individual probabilities are, you need to get 1. Right? Is there any question about number 2? How about number 1? What's this say? For each value of X, you can never have a probability which is greater than 1. And that's also true, right? You don't say the probability that someone has 0 cars and doesn't own a car. The probability that somebody doesn't own a car is 120%. Right? You never say that, right? That doesn't make sense. And also, you don't say that the probability that somebody doesn't own a car is -2. Right? That also doesn't make sense. So it has to be what? Between 0 and 1. Right? Every individual probability has to be that. Okay? So the probability distribution of a discrete random variable possesses the following 2 characteristics. So these are 2 statements we can make about probability distributions. Okay? So this is a picture of that same probability distribution. What do I mean by that? What's the horizontal axis here? And what's the vertical axis? What's the horizontal axis? These are the different values that X could take. And what was X again in this last example? The number of cars people own. And what are the different values that X could take in that example? Well, they could own no cars, or they could own one car, or two cars, or three cars, or four cars, right? So X here is the different values that that random variable could take. And what is the y-axis here? What's the y-axis? The probability for each of these. So what was the probability that someone had no car? It was 1.5%, right? So this bar will have that height, 1.5%. This is 10% up here, right? So this is down here. The probability that someone had, whatever, I don't remember, but I think this one was 8.5%. Okay, so this height would be here. Okay, so this is just a graph of that other table. This is just a graph of this table, right? The height of 0 is 1.5%. The height of 4 is this, right? And so on. So this is just a graph of that. So this is a graph of the probability distribution, right? This is a graph of the probability distribution. So what can you see by looking at the graph? Well, one thing you can see is what's the most likely number of cars that a family will have? 2 cars, right? So you can see something from this picture, right? You can also see what's the smallest probability? 0, right? So a graph shows you this visually, right? And it's nice to have visual instead of this, right? How many people prefer this representation? And how many people prefer this one? Well, it's kind of a silly question, but they both have, they're both useful, right? This one is useful. This one tells you the actual numbers, but this one gives you a feeling for what it looks like, right? So they're both useful. Okay, any questions about that? So, yes?
Can you actually mark the probability of each column?
Yeah, of course you can, yeah. So, yeah, that would make it, maybe, it would make it more clear, but also might clutter it a little bit, right? So both, you know, some people say, oh, I want to do that. Some people say, no, let's not. Anyway, okay, example 5.2. Let's see. I think we'll take a little break from this, and we'll come back to this in a second. In my other class, we started to do group work. And I'm sort of, this is a push at APU. They're trying to ask professors to ask courses to have group work, because apparently that's a new type of learning that you don't like it.
Even for the statistics?
Yeah, you can do. I'm even doing it for my math class. So statistics, you can do it. And it worked actually pretty well. I was surprised. It seems to work in some good ways. But I don't think I'll do that right now, because I didn't prepare anything for that today. But maybe next time we'll do it. The only problem with it is that it takes time, and it takes kind of this. If I want to keep going, it slows me down. But on the other hand, it has some benefits. So I'm not sure if the benefits outweigh the negative points. But anyway, so but right now, I'll just ask you to do one thing, and that is put on your earphones and listen to one video that I made on YouTube, chapter 2, section 1, or part 1 rather it's called. So it's going to be here, chapter 2. R, you have to search for R, I guess, I don't know how you search. Either you look for this account, yes to that, and then look for all of them, or maybe you can just type in this name and that will find it for you. Actually, I'm not sure if this is public enough, whether you can find it. It's public or public, yeah, it is public. So, okay, so you can look at this, you can find it's called R in Action, Chapter 2, Part 1. Now, before you do it, I don't know yet, open up R as well on your computer, or while you're watching it, open up R and try some of this if there's anything to try. Forget about this first video, but take a look at this. So when you get to this part here, which is about minute 3.5, try this example here when you get there, after at minute 3.5. Or this one here. Okay, so example 2, 5.2. Each of the following tables lists certain values of x and their probabilities. Determine whether or not each table represents a valid probability distribution. Now what they're asking you to check here is these two laws, these two facts. That is that the probability always has to be between 0 and 1, and the sum has to be equal to 1. So here, they give us 3 possible random variable and probability distributions, and they say, are these so-called valid probability distributions? So what about that? So what about the first one? So here are the values that it can take, and here are the probabilities. So is this valid or not valid?
Invalid.
Well, he says invalid. Why is it invalid? What?
The sum of
The sum of
the possibilities should equal
the possibilities or probabilities should equal what?
1.
1. And what does it equal here?
No.
Not 1, okay. What is it, 18, 19,
Uh,
58, 85, 85, yeah. Okay, so that's not, the sum of this is not 1. Okay, good. So that's not, we couldn't say this is a probability distribution. Not a valid one. Okay, how about this one?
Yes.
Okay, he says yes, and none of them are negative, none of them are greater than 1, and the sum of them is 1. Okay, good. How about this one?
Invalid.
No, it's valid because why?
Negative.
The probability of 9 is what? Is written as negative 0.2, and that's impossible, right? Okay, so it's not a valid probability distribution. So here are the answers. Okay, the following table lists the probability distribution of the number of breakdowns per week for a machine based on past data. So, we have a machine, it doesn't always work, right? It's breaking down, then they fix it, it breaks down again, they fix it, right? So maybe it's like some machine in a factory, right? So they have to fix it sometimes. So, and this is number of breakdowns per week. So what's the maximum number of breakdowns that have occurred per week? 3, right? And what's the minimum number of breakdowns that have occurred per week? 0. Okay, is this a discrete or a continuous random variable? Discrete, because what are the possible values that this random variable can be? 0, 1, 2, or 3. That's discrete, right? Okay, and then we see the probabilities. What number of breakdowns per week is most likely? How many breakdowns per week are most likely? Like if I take this week, what would I say is the most likely number of breakdowns I'm going to have this week? 2, right? Right? Why is that? Because the probability of 2 is what? 35%, and that's higher than the other ones. Okay? All right, everyone agree with that? Okay, present this probability distribution graphically and find the probability that the number of breakdowns for this machine during a given week is exactly 2, and then some other ones. So how do we make it, how do we present it graphically? We just make a graph where the x-axis is what? 0, 1, 2, or 3, and then we give the probabilities for 0, 1, 2, and 3. Right? So what do we get? We get that. Okay? Everyone agree with that? So this is a graphical representation of that probability distribution, and here we can see that what's the most likely number of breakdowns? Again? 2. We can see it obviously, right? Okay? All right. Now the other part B, the probability that we get exactly 2. So what is that again? Probability that we get exactly 2 is 35%. Now the other questions are a little more interesting. The probability that we get between 0 and 2, or from 0 to 2 breakdowns. So what's that? The probability that we get from 0 to 2 breakdowns. What is from 0 to 2? What does from 0 to 2 mean? From 0 to 2 means 0 or 1 or 2. So when you have that or, that means you need to add up the probabilities for 0 plus the probability for 1 plus the probability for 2. Okay? That's what or means, right, basically in English, right? So the probability from 0 to 2 breakdowns is the probability that x, the number of breakdowns, is between what? 0 and 2, right? That's what we're asking. And it says equals 2. So, okay, so we say, what's the probability that x equals 0? And then we say, what's the probability that x equals 1? And then we say, what's the probability that x equals 2? Is everybody comfortable with this notation? Because when I studied this, I was completely uncomfortable with this notation because I saw x equals 0, just confused me. I couldn't read it. But it just means, it means that this, actually the clearest way to think about it is whenever we ask for a probability, we always need to put an event inside. So it has to be the probability of some event. So I usually like to write it like this. The probability that x equals 2, that looks confusing to me. But if I do this, then I said that means to me this is the name of an event that x equals 2. If you don't need the quotes, then you don't need the quotes. But for me, it just makes it more clear that I'm talking about the probability of an event. What event? That x equals 2. Okay? So, what is that probability of that event? What is the probability that x equals 2? 0.35, but that's not the only number we need. We need probability that x equals 1 and the probability of x equals 0. So it's 0.35, 0.20, and 0.15. So we add that up, and what's the probability that there are between 0 and 2 breakdowns? 70%. Okay, is that clear? How about the next question is what? More than 1 breakdown. What's the probability that we'll have more than 1 breakdown this week? Right? So what does more than 1 mean? 2 or 3, right? So we need, so there's that word or again. 2 or 3, so or means what? Add them. Okay? So 2 or 3 means 2 plus 3. So the probability that x equals 2 plus the probability that x equals 3. So 2 was 0.35 and 3 was 0.30. So we add those together and we get 0.65. Okay, the last one in this question was at most 1. So what does that mean in English? What's the probability that we'll have at most 1 breakdown this week? Means that we'll have no breakdowns, that would be at most 1, or 1 breakdown. So 0 or 1, and there's that word or again, and or means that you add, so you get 0.15 plus 0.20. Okay? Because it was 0.15 plus 0.20 there. Okay? Any question? Okay, example 5.4. According to a survey, 60% of all students at a large university suffer from math anxiety. How many people in this room suffer from math anxiety? Math anxiety. You have math anxiety? Nobody? Okay, so if it's nobody, then what percent of our students have math anxiety? 0%, right? If you all answered honestly. Okay? But according to a survey, 60% of all students at some large university do suffer from math anxiety. But we don't have a representative sample here because maybe the students in our class that suffer from math anxiety didn't come to class today. Right? So you guys are not representative of the actual class because you came. So maybe you're not as, right? You think you might, okay. Okay, so then it's 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1 out of 13, but, okay, so, but anyway, even that's not representative, right? Because some students didn't come. And they may be the ones that have more likely to suffer from math anxiety, right? Probably, right? I'm not sure of that, but, okay. So according to a survey, 60% of all students at a large university suffer from math anxiety. 2 students are randomly selected from this university. Let X denote the number of students in this sample. How big is the sample? We're just selecting 2 students, so the sample is how big? Just 2, right? Understand? Let X denote the number of students in this sample who suffer from math anxiety. So X is a random variable, and what values can it take? 0 or 0, 1, or 2, right? In our sample, we might have 0. We might have 1, and we might have 2, right? And what's the probability that a person selected at random will suffer from math anxiety? It's obviously 60%, right? Okay, so we have a random variable, and we have this number, 60%. Let us define the following 2 events. N equals the student selected does not suffer from math anxiety. So N is that event. And M is the student selected suffers from math anxiety. So what is the probability that X equals 0? That is the probability of NN. What do they mean by NN? They mean that the first person selected is not, and the second person selected is not. Okay? Now, NN means N and, I'm using the English word and, A-N-D, N and N. Right? N and N, not N or N. Okay, it's N. Okay, what is the probability that there's one person? That means we have an NM, or we get an MN, right? Is this clear? Is that clear? And what's the, what's the probability of NN? Where does this number come from? I guess it comes from this here. So NN, the first student is 40%, and the second student is 40%. So we get this. Okay, so that's where this comes from, right? And how about this? How do we do this one? We figure out this one, and we figure out this one, and what does OR tell us to do? To add. OR tells us to add. So, we want NM and MN. NM is 40-60, and MN is 60-40. Both give me 24, and I add those up, you get 48, right? So what's the answer to this one? 48. Okay? And how about this one? The probability that X equals 2. That means what? 2 math anxiety students. So that's MM. So what's the probability of MM? MM. 36. Okay? So we've just calculated the probability that X equals 0, the probability that X equals 1, and the probability that X equals 2. But those are all the different values that X can take. Those are the only values that X can take, right? Because we only have 2 people, so the least number of math anxiety students we could have is 0, and the most number of math anxiety students we could have is 2. So we have 0, 1, and 2 as the possibilities. So now we have the values that x can take and their probabilities. So now we have discovered, what is it called? Now we have discovered the, what's it called? The probability distribution for this random variable. And here's what it looks like. 0, 1, and 2. What time is it now? 7 minutes? 12 after, 7 minutes after 12? Okay, so we still have 3 minutes. Okay, now let's look at this horrible thing. Okay, how do I express the mean of a set of numbers? What's the symbol for the mean? Do you remember? X bar or mu, right? And here I see mu again, right? Okay? All right. What's the difference between X bar and mu that you learned before? Mu means comes from the population, and X bar means it comes from the sample, right? So somehow they're using mu here, so maybe they mean something similar to a population here, but it's not clear yet, okay? But it is something to do with like the mean, okay? Now though they're talking about, but then, before today, you didn't know what a random variable was, right? Unless you studied it somewhere else, right? We didn't study random variables yet. So before we were talking about means of sets of data, right? But now we're going to talk about something else called, we're still going to use the word mean, but it's really a different thing. We're talking about the mean of a random variable. So, going back to this problem here, what might we mean by the mean of this random variable? Remember, this random variable is tossing 2 coins, and x is the number of heads, right? Now, there's no data set here, right? I'm not giving you a data set and saying calculate the mean, right? I'm not giving you a bunch of numbers and saying calculate the mean of this set of numbers. So it's not the same question as before. And the word mean, I'm stretching it to another meaning or to a new meaning, right? It's not the same as the other word, because the other word mean was for a set of data. We don't have any set of data here. So it's a different word, but we still use mean. Okay? So what might we mean by that mean here? So this is the number of heads. Now what are the possible values? 0, 1, and 2. Okay? Now, what do anyway, we don't have a meaning for this question yet. I'm just asking you what you might think it means. But they're going to have a specific meaning for it. But here's what it means basically. In this experiment, we could do this is the probability distribution for tossing the coin, just tossing 2 coins just one time, or tossing a coin twice, but just doing that one time, right? But we could do that 100 times, right? I could take 2 coins and throw them down on the table and count how many heads I have, and then then collect them again and throw them down on the table again and count how many heads there are, and then do it again and count how many heads are, and do it again and count how many heads are, and do it 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 100 times. So sometimes I would get 0 heads, right? And sometimes I would get 1 head, and sometimes I would get 2 heads, right? And now I actually have a set of data, right? Because the first time I got 0 heads, the next time I got 2 heads, next time I got 1 head, next time I got 1 head, next time I got 1 head, next time I got 0 heads. So I could say I actually have a set of data now, 100 points in my data set. Okay? If I did that, and then I took the average of all those experiments, what would you guess the average would be? So sometimes I'll get 0s, sometimes I'll get 1s, and sometimes I'll get 2s, and I ask you to average all of that up, what would you guess that average would be? Does anybody have any intuition on that?
Close, somewhere near 1.
Close to 1, exactly. Doesn't everybody agree with that? Going to be approximately 1, right? And that's what we're going to mean by the expected value of a random variable. Now, I'm not saying you just do it 100 times. I'm saying if you just kept doing it forever, what would the mean get closer and closer to? It would get closer and closer to 1. And that's what we mean by the mean of a random variable. So that's different than the mean of a set of data. And we're stretching that word. It's really a different word, but the concepts are so related, right? And they seem so similar that we'll still use the same word, but they're not the same. It's not the same word, and it's not the same concept. Okay? But that's what we mean by the mean of a random variable. Now, it turns out that this calculation right here will give you that value 1. We just agreed that it's going to be 1, right? That we think it's 1. Now let's do this calculation and I'll show you that you're going to get 1. And then maybe next time we'll talk about why that works out that way. But it says what? Sigma x p of x, right? So when you do sigma x p of x, how many x's are there here? 3. And so you just take the x times its probability, right? So what's the first x? 0 times its probability is what? 1/4 plus, then you take the second x, what's the second x? 1 times its probability is what? 1/2 plus you take the third x, what is that, third x? 2 times its probability, 1/4. And what do we get? We get 1/2 plus a half is 1, right? So it turns out that this gives us, now we can justify this a little bit more clearly later, but it turns out that this calculation will give it to you. Now it doesn't have to just be for this experiment, it could be for any x, any random variable that we've talked about so far. It could be the sum of the dice, sum of tossing 2 dice, it can be all the other things that we talked about. Okay, this will be our definition actually of what we mean by the mean of a random variable. And that is not the same as the mean of a set of data. Okay? Okay, so random variables allow us to jump into more theoretical types of discussions than we could with just data sets. Okay, so now, from now on, things will take a turn towards the more theoretical because we have this random variable concept which allows us to do that. Okay?